In this video, we'll be studying about force on dielectric, okay, which we'll be studying about the effect of fringing electric field, or you can say the edge effect or fringing electric field. I think this topic is not in the JEE mains. I think it's a part of advanced fringing. Okay, what happens? Firstly, just know what this fringing electric field is. See, these are the plates of capacitor. Okay, they are charged. Let's say this surface or this side has positive charge, this side has negative. Then see there develops. See, you know that there will be a electric field inside it. Okay, in this direction, right? Now, what will be the nature of electric field on the edge of the capacitor? Actually, the nature is somewhat like this. Okay, the electric field originates from here. Okay, and they came here. Okay, somewhat like this. They originate from the positive plate and ends at the negative plate. Okay, this phenomenon, okay, this phenomenon is known as edge effect, and this type of electric field, this is known as fringing electric field. Means the electric field at the edge of the capacitor, that is what fringing electric field. And due to this edge effect, when a dielectric is inserted or placed near a charged capacitor, then due to this fringing electric field, the dielectric slab will experience a net force towards the capacitor or inside the capacitor. Okay, but when slab is fully inserted, the net force will be 0. How this force come into play? Let's see via a diagram. Okay, let me raise this. Okay, let it be. Draw another diagram. This is your capacitor. Okay, this surface is having charge, positive charge, and the other surface has negative. You know that there will be fringing electric field on this part. Okay, it will be somewhat like this. Okay, now suppose this is a dielectric slab which is placed near the surface. Okay, see, if this is a positive charge, then the charge induced on this part will be negative, and if this is a negative one, the charge induced will be positive. Okay, now what will be here? Here the electric field will be in this direction. Suppose this is a parallel direction. Let's say it is E parallel, and this is a perpendicular direction. Let's say E perpendicular. Okay, now this dielectric slab, this part of dielectric slab will be experiencing a force towards this side due to this E parallel, because it is a negative charge and electric field is in this direction. The force will be in this direction. Okay, you can say Q into E parallel, and this due to the perpendicular electric field, the slab will be experiencing a force to this side, and this will be Q into E perpendicular. Q is the charge on this plate of the dielectric slab. Similarly, here the electric field will be in this direction, and this will be the direction of E parallel, E perpendicular, and this will be direction of E parallel. So here this side will be experiencing a force Q into E perpendicular, and this side it will be experiencing a force Q into E parallel, right? So you can see this component, perpendicular component, Q into E perpendicular, Q into E perpendicular, this will cancel out each other. So you can see that the net force will be inside, the direction of net force will be inside of the capacitor, right? This is how the dielectric slab experiences a net force inside the capacitor. Okay, so and the you can say dielectric constant is okay. Now we need to find the force, this magnitude of the force. Okay, we are doing all these things to find the magnitude of force. We need to find what will be the equivalent capacitance. Okay, these things we need to find. Okay, now firstly we'll be finding the equivalent capacitance of a partially filled dielectric. Okay, here we are considering the edge effect. Okay, to your dielectric, okay, other case. Okay, suppose a dielectric is partially inserted, somewhat like this. Just consider it straight. Okay, but due to the writing pads, figure is not much clear. This is a dielectric slab. Okay, which is partially filled inside the capacitor. Right. Suppose this is a x, means the x length of the dielectric slab is inside the capacitor. Suppose this is b, and distance between plates of capacitor is, let's say, d. Okay, this dielectric constant, let's say, k l. Okay, also consider this side as the positive charge on this side of the plate and negative charge on this. Now what you are seeing here a dielectric is inserted having dielectric constant k. So let's say its capacitor is, let's say, it is k. Okay, and having dielectric constant c2. So you can redraw this figure somewhat like this. Okay, this here, this is, you can say, this side, and this side you can see here. Okay, now you can see these two are connected in parallel. If you look this figure, if you make it like this, okay, that this is a dielectric slab, okay, and this is a normal air. Okay, suppose this capacitance is c and this is c2, c1 and c2. c1 will be epsilon naught into a will be this length multiplied by this width. Okay, it will be b into l minus x upon d. This will be the value of c1. c2 will be, since it is a dielectric, it will be k into epsilon naught into a. A will be x into b. What will be this area? This length multiplied by this width upon d. This will be c1 and c2. So you can say the c equivalent, that is, it will be between a and b. You can say this is point a, this is point b. Here it is point a and this is point b. Okay, c equivalent will be c1 plus c2. That means epsilon naught b upon d L plus x into k minus 1. This will be the result that will be coming. The equivalent of a capacitor which is partially filled with the dielectric constant k. Okay. You can also find dc by dx. It's a very important result. Okay. Which we will be using in solving numericals. K minus 1. This will be dc by dx. Okay. Now we'll be studying two cases. We'll be finding force two cases. The case one is when battery remains connected during insertion. Okay. The second case is when a battery is disconnected. Okay. When battery remains connected, your U will be 1 by 2 into C into V square. Okay. And you know F is minus du by dx, and this will be put the value of U. It will be V square by 2 dc by dx. And you can put the value of dc by dx from here. From this equation we have got this value. Okay. On putting this value, you will get F is equals to V square epsilon naught B upon 2d into k minus 1. This will be the value of force when battery is connected. Means which force? Which is responsible for the net effect which is responsible uh, for the pulling of dielectric inside the cap stack. Okay, the case number 2. Case number 2 is battery is disconnected. Okay, U will be Q square by 2C. Okay, F will be minus du by dx will be Q square by 2 to d dx of 1 by C. Okay, so this will be F is equals to Q square by 2 into ddc of, you can write this as ddc of C inverse into dc by dx, right? And on putting the value of dc by dx and solving this equation, you will get F is equals to Q square by 2C square epsilon naught B upon D into K minus 1. This will be the value of force when battery is connected. Okay. And one more thing, important thing, that in this case, slab will perform periodic motion but not SHM. Slab will perform. This is a very good question. Can be asked the exam, okay? But not SHM. Right? So this was our last topic of this chapter, course on dielectric. Okay. Practice problems on all the topics that we have covered in this chapter. Okay. Well done. Thank you.